talk to you about heating curves. We're going to take some time and we're going to label parts and we're going to see all the type of questions you're going to have to answer about this. So as I'm going through this, you should be looking at your own heating curve on your note packets. And you should be copying stuff that I'm writing down because this is the kind of stuff you're going to be asked about on tests and quizzes. Okay, so the first thing that we're going to look at, we're going to look at what's going on with this graph. Okay, the first thing is that on the y-axis, we're looking at temperature change. So you can see, as we go up here, that means the temperature is increasing. Now, down here is we're adding heat. So it's on a stove, it's on a hot plate. We're adding heat to the system. And you can see, for the most part, as we add heat, what happens to the temperature? That makes sense. As we add heat, the temperature goes up. But do you see that it's not always increasing? Isn't that interesting that we can continue to add heat? But at points, that substance doesn't increase its temperature. So we're going to talk about exactly why that is, okay? The other thing I want to talk about is you could call this the cooling curve if you were going in the opposite direction. So you could add heat, but if you're taking away heat, do you see how the temperature ultimately would be decreasing if you went in the reverse? So that's something to think about. Okay. Now, the first thing you're going to be able to have to do is label all the parts of this graph. And this is how the heating curve looks for almost every substance. Almost every substance looks this way. Down here is where you're at the coldest, and we actually have all three phases of matter on here. So when you have your coldest temperature, what is your substance? A solid, a liquid, or a gas? Yeah, it's a solid. So we're going to label this part right here as the solid, and the lowest diagonal up is always going to be a solid. Okay, as we add heat and add heat and add heat and add heat, it's a solid. It keeps heating up. What eventually happens to a solid? What eventually happens to a solid as you get high enough temperature? It's going to start melting. It's going to start melting. So this straight line is actually a phase change. All the diagonal lines are going to be our three phases of matter. Our straight lines are going to be our phase changes. So this would be melting if it's going this way, and it's freezing if it's going this way. Okay, when it melts, what is it then? It's a liquid. Okay. Then, as we keep adding heat, the liquid keeps getting hotter and hotter and hotter. And then once it gets to a good temperature, the perfect temperature, at that point it's going to start boiling or vaporizing. Do you guys remember what it's called if you're going the opposite direction from a gas to a liquid? That would be condensing. So if it's cooling, it's condensing at that point. Then, once it's boiled, at that point, it's a gas. There you go. So, let's look at this then. Now, from now on, you've got to know solid, melting, liquid, boiling, gas. Okay? This is how all heat curves are going to look. Now, let's look and see what's happening here. As we add heat to a solid, what happens to its temperature? Increases. Look, what is happening to the temperature as the substance is melting? We keep adding heat, but we're still right here in the same temperature. So do you see here that during phase changes, temperature is constant? That is a key point. Key point. During phase changes, do you see how I'm taking the time to write this? That means you should write it too. During phase changes, temperature stays constant. Okay. Now, you see liquid, now it's a liquid. It's no longer changing phase. Now, as we add more heat, now the temperature is increasing yet again. But once it starts boiling, do you see what's happening to the temperature? It's staying the same. Now, here are some other things I need to label. Let's look at this point right here on the graph. Right here. This point right here is the temperature at which something melts. It's the temperature at which something melts. Do you see what that is? It is the melting point. Yay! Whereas this temperature right here, right there, is the boiling point, because it's the temperature at which something boils. I think I ended up a little too high on that. It's the temperature at which something boils, right there. Boiling point. Melting point, boiling point. That's the actual temperature, so it's on the y-axis. Okay, let's also talk about, so key point here is during phase changes, temperature stays constant. So let's talk about kinetic versus potential energy. You remember it from the gas laws unit, so it was a couple units ago, that kinetic energy increases as temperature increases. Remember, as those particles move faster, the temperature goes higher. So kinetic energy is directly related to temperature. So we have to look at the 3 points. Let me label these as A, B, C, D, and E. So when you look at these, what points have the temperature changing? You see that? Is the temperature changing as we add heat to a solid? Yes. So kinetic energy is definitely changing at A. Is it changing, is temperature changing as we're melting or freezing? No. No, so kinetic energy is not changing here. Why? Because kinetic energy is directly related to temperature. As the substance a liquid and as we add heat, is the temperature changing? Yes, it is. What about here? Is the temperature changing? Yep, and I skipped this phase change because if you look here, no temperature change. So we aren't increasing kinetic energy. So as we go through, anytime the temperature is changing, we're also increasing kinetic energy. If we're decreasing the temperature, we're decreasing kinetic energy. Why? Because temperature, the definition of it, average kinetic energy. And if our average kinetic energy is changing, therefore, our temperature is changing. Those go hand in hand. So let's think. If we're adding temperature, we're adding heat to this system here. We keep putting more and more and more heat in, but we're not actually increasing the temperature, so we're not increasing kinetic. Where is that energy going? It ends up being potential. Let me show you why. Do you remember when I made you guys all act out the particles with your fists? Solid particles looked like this. Liquid particles looked like this. Wouldn't you agree that it looks like the liquid particles have more energy? Here's liquid, here's solid. So that is not kinetic energy because from here to here they have the same amount of temperature, so the kinetic energy stayed the same. Instead, we're changing the potential energy at B and D. So you need to memorize this, better yet understand it, but at least you know kinetic energy changes at the 3 phases. Potential energy changes when the phase is changing. Why? Because the kinetic energy is directly related to the temperature. Okay, there's one more thing I want to show you here. 2 more things to label, and we're going to discuss it a little bit. Okay, there's two new words right here. That is delta H of fusion. Whereas this right here is the delta H of vaporization. Now, I'm going to erase my stuff about potential and energy, potential and kinetic energy, so I've got some room here to talk about delta H and delta H of fusion, delta H of vaporization. Delta H of fusion is the amount of heat required to melt, put a space there, to melt a substance. Whereas delta H of vaporization is the amount of heat required to boil something. So that's, if you look here, the amount of heat we need to add to get it from a solid to a liquid is this right here. That's delta H of fusion. Now usually it's per gram, but right now we're kind of not talking about a specific substance. That's why I left it kind of open-ended there. Delta H of vaporization is the amount of heat that we would need to add in order to get this substance from a liquid to a gas. So that's yet another way that we could label this graph, this curve. Okay. One last thing. As we are moving this way, are we adding or taking away heat? Yeah, we're adding heat. So when we melt and when we boil, delta H of fusion, melt, delta H of fusion is going to be positive. Why? We have to add heat, okay? When we freeze, do we add or take away heat? When we freeze, we take away heat. So it'd still be the same value, but all of a sudden it'd be a negative number. That's the same thing with boiling. Delta H of vaporization would be positive, and delta H of vaporization would be negative if we're condensing. So let's think about this in other terms. Melting, you have to add heat. Think about it. In order to get ice to turn into a liquid, we'd have to put it on a stove, let it sit in the sun. We are adding heat to the system. That is endothermic. In order to get something to freeze, we have to put it in the freezer. We have to remove heat from it. So that means heat is being released. It's an exothermic process. Boiling, you have to put it on the stove, right? You have to add heat. That's endothermic. Whereas condensing, we have to remove heat. We have to cool it down. And therefore, that's exo. So I quickly went over this, but you've got to know the 4 phase changes, and there's a few others, sublimation and deposition. Make sure you know those too. And if they're endothermic and exothermic processes, and what happens to delta H on those.